Okay, now you saw lessons about the Arrhenius equation, and I want us to work through an Arrhenius equation together in class. This is worded in a challenging way for students. I want you to, pause and write this question down, and then I want you to think about what I have underneath there, okay? So let me explain it. You pause it, you come up with your answer, and let's see if you got it correct before we proceed. So in this problem, I know that it says that the rate constant doubles for every 10-degree rise. That's very common for a lot of reactions. You raise the temperature 10 degrees, it goes twice as fast, okay? Now, if the reaction is going twice as fast from temperature, the temperature change is played out in the value of its K. So its K is actually doubling as well, okay? So if the temperature is doubling the reaction, it's actually doubling the magnitude of K. All right, so now we're going to consider this scenario down here. K1 is at 295. It's the slower rate. K2 is at 305. It's the faster rate. So I want you to think about which one of those statements is correct. A, B, or C. Pause it, ponder it. Decide for sure which one you think it is. Rejoin me and let's see if you got it right. All right, this really throws students off a lot. The answer is C. 2 times K1 is equal to K2. Students get that wrong very often, but let's think about it. Which one should be bigger, okay? K2 should be bigger than K1. Is that correct? K2 should be bigger than K1 because you're raising the temperature. The K2 is the bigger one. So a lot of people say, well, if you double, the opposite. I think B is what a lot of people say. They say, well, it's twice as big, let's put the 2 in front of it. We want to make these equal. So if I double the size of K1 because it's half as big, it will end up giving me the value of this. So that is a relationship that we can use when we don't have real numbers for our K in our Arrhenius equation. But you got to be careful what you do here. If the rate is doubling, the K is doubling. If the K is doubling, twice the smaller will give you the bigger. All right, so let's pull out the Arrhenius equation. Natural log of K2 over K1 is equal to negative E sub A over R, okay? And then we've got our T part. I'm going to make my pen give me a little more flow here. 1 over T2 minus 1 over T1. So that's a matter of plugging in what we know and solving for what we don't know. Here is where we'll use this information because I wasn't given real numbers to plug in. If I was, I could put in those values of K, but all I was told that it's doubling. So in place of the K2, I will put 2 times the K1. It doubled, so it's twice as fast. I don't do any replacement for the bottom one, and the K1s cancel, and I have the natural log of 2 is equal to negative E sub A, which is what I'm trying to solve for. It says, use the two-point Arrhenius equation, which is what this is. We're going to calculate the activation energy, so that's what I'm solving for. The R that we use in this case is the 8.314 because it's the one that has the energy unit of joules. The big place that you could mess up is the correlation between the K1s and the K2s. We know that the K1 is the low temperature and the K2 is the high temperature. So I'm going to put 1 over the high temperature, that's the K2, the higher speed, over the lower temperature. Okay? When I solve for our value there, let's see if I've broken it up in my notes here. Yes, the natural log of 2 is 0.693 is equal to negative E sub A over 8.314 joules per mole Kelvin. And this part, when I do the work here, is equal to a negative 7.7 times 10 to the minus 5. And these are kelvins. I should have written them in. So the unit for that is 1 over Kelvin. So I'm working my way to solve for E sub A. I'll talk you through it, and then you can do it. E sub A, I'm going to need to get the negative over here. That negative and that negative will go away, so activation energy is positive. Activation energy is always positive. It is always a mountain to climb. It is never a valley, so it's always positive. Okay? I'm going to multiply by the 8.314 joules per mole Kelvin, and I'm going to divide by my value here, and that's going to give me an activation energy equal to 7.48 times 10 to the 4. Well, what's the units? Well, the kelvins are canceling, and that leaves me with joules per mole. Very often we report activation energy in kilojoules per mole instead. So we'd say, well, I don't want the joules, I want the kilojoules. I would divide by 1,000, and that would give me a 74.8 kilojoules per mole. It is a positive number. Activation energy always is a positive number, and it's very commonly reported in kilojoules per mole because that usually gives you in the 100 kilojoules per mole range. It's a little under. You might have 200. You might have in the hundreds value. It's common for that. So once you do several, you start getting the familiarity to what is common, and that's why they usually report it in kilojoules per mole. All right, so that is an example problem of using an Arrhenius equation where we have the little quirk of instead of them giving me K values, they are giving me how it's affected. If it said it tripled, I'd put a 3 here, okay, as the temperature rises. But doubling is a very common relationship. But if they give you real numbers, you can put those real numbers in there, and that's always dandy. Lastly is you could have to solve for any sorts of things here. If I gave you activation energy and a couple Ks, I could say, well, what temperature is going to give me that new K? Or if I gave you temperatures, I could solve for a new K with both temperatures given. So any one of those variables you have to be able to solve for. For some students, they have to practice that algebra because it's something you have to pull back forward. It's something that we use a lot, is being able to solve an equation similar to this for any one of those variables.